you, you will be in trouble. And more importantly, we will be in trouble. We have a good relationship here at the hotel. Much as we love the Alexis Park, I would rather not go back to the Alexis Park. It is not a lot of fun doing CPR on somebody in 110-degree weather. Please don't send us back to the Alexis Park. Or I promise you, you and I will sit down and have a little talk. Okay, guys? Be responsible. Be adult. Get your friends to go pay their bills. Thank you.
Okay, so it sounds like someone's fucked up. Yeah, let's please not go back to the Alexis Park. Right, so that was the bytecode format for PYCs. All those formats come out standard as Python. Then optionally, a lot of people are using packaging. Packaging allows you to distribute a runtime along with your Python code. It means that people don't have to have the version of Python which you need to be installed on their system to run your code. So pyToExe, pyToApp, they're all examples of packages. So they'll take your code, runtime code, bundle it up, and allow it much easier to run just with a double click. This is important because it means that developers can distribute a modified Python runtime along with their code, and a lot of the anti-reversing techniques that we'll talk about rely on the fact that they can distribute that modified Python runtime. We're going to speed up. So this is the object hierarchy. We're going to blast through this. Obviously modules, the only thing to note is that a module doesn't have a code level object. It doesn't have a code object once you've imported it. This is for speed reasons. Once it's imported, it's not needed. So it's a language design issue, but from reversing, it's a real pain in the ass. There's obviously then there's the class level objects. All the superclasses to a class are in underscore bases. Classes have methods. Methods are literally just a wrapper for functions. The functions held in the IAM func object. Functions have a func code object. The code objects, which is actually what we care about, has various attributes. It's a very verbose code object. You can tell a lot about how the code will run. The biggest one is the CO code object. That's actually a string representation of the bytecode, so we're going to be able to access that and start reversing things out. And then there's all these attributes here that, constants and variable names, the line numbers that stuff was, the function was instantiated at, all really useful information as we get into some of the techniques. So all you need to know is that from all the Python objects, like the code is the one that we're really going for, and everything else just stacks into that. So we've blasted through this pretty quick. Python has bytecode language. Obviously, it's a pretty simple language, and every opcode just is an 8-byte opcode. So there's only 256 available. Currently in Python 2.6, there's 113 already defined. Optionally, one Python opcode can take arguments. All arguments are 2 bytes. So if this is a Python source, just print bugs. When it goes into its bytecode instructions, you can see there, these are the different instructions names. Each of those will map to a single integer, just a mapping between a number and the instruction, and some of them take arguments. And this is the byte stream, so you can see that 64 would relate to load const, and it took 2 arguments, both of which in this case were null. Well, one argument, and one argument is always 2 bytes. Oh, fail. Okay, so we blasted through the Python. We're going to run through this and then actually get onto the new techniques. The existing stuff that's available, disassemblers. There's dis that comes standard with Py. The representation that you saw from source code to instructions, that was just done using dis. It will just dump out the bytecode for you. The important thing is it relies on opcode.py, which is the Python level module which gives you those number to instruction mappings. Oh, fail again. So there's debuggers. PDB is a standard Python debugger. It comes again with normal Python, but it's very much a developer's debugger. It assumes that you're going to have access to the PY. It is for finding bugs as you're developing, as opposed to finding bugs in other people's code. So that was what I based a lot of my stuff on, but extended it up to be more useful when you haven't got access to a PY file, only the PYCs. Decompilers. There are a bunch of decompilers, some of which are an application that you download, some of which are an online service. Why you'd want to use an online service to decompile and give the people your source code, I don't know, but people obviously do. Some are free, some are commercial. They do definitely vary in quality and depending on what version of Python you're running. The best free one that I found that I based a lot of the stuff that we'll talk about in pyREtic on is Unpicy, from a Russian developer. It's not perfect, but it's good enough in most situations. For the online services, dpython is certainly the best. The quality of their decompilation is really good, but it's not free and you're giving them your source code, so it's up to you. Bytecode assemblers and modifiers. Byteplay and bytecode assembler are certainly good ones. Antifreeze is an example that we've already spoke about for PYDs. These allow you to work at the Python bytecode layer rather than at the Python source layer. If you're interested at the kind of this level of Python, they're certainly good to play with, and you'll learn a lot more about how the Python runtime actually operates by playing with them. So that's what exists so far. What are the anti-reversing techniques that I was seeing in a lot of these commercial apps? So we're going to go through, blast through a taxonomy. Like I say, increasingly commercial and closed source apps put in obfuscation techniques in to stop you getting at their pie, because obviously, you know, they've put their effort into capitalizing on that, and there will be a bunch of bugs in there. The more effort that they go to keep the source away from you, the more you know there's going to be bugs in there. I've worked with Python a lot, and there was a bunch of different techniques that I've seen, so we're going to blast through these techniques. All of these techniques mainly focus on when the bytecode is on disk, when there's those PYC files on disk. All the techniques focus on obfuscating that PYC file, so you can't, making it so it's not in its standard form. So all the basic tools that we've just talked about break. And that's pretty much the approach that everybody's taking. So the simplest one that you see a fair amount is just hiding in the packages. You know, the pyExe, pyApp. People believe that if they wrap their code in that, then you can't get access to it. Obviously, it's standard formats. It's easy just to reverse out. Often you'll find a packager, and maybe even the PYs will be present in that. So that's super easy to get by. You often see this on Windows 32 applications. People will package it up into a PYD and assume that you can't get access to it. But it's a standard documented format, so it's very easy to just reverse out. Source code obfuscation. I've never actually seen this used in a real application. There's a commercial application that is sold to do the obfuscation, but I've never seen anyone actually use it. It's a similar kind of thing that you see in JavaScript malware, where they'll try and make the source code look complicated. The functionality will be the same. So for example, there's this kind of easy code on the left, and it goes to this kind of weird obfuscated code on the right. I'm sure it's very easy to actually undo what they've done. I haven't looked into doing it because, like I said, I've never seen it in a commercial application, so I haven't tried. When I was looking at the guy who sold this Python obfuscator, though, I found a gem. And he also sells PoreSense. PoreSense is a way to cat-proof your computer. And it will tell you when cat-like typing has been detected. So if people have kind of cat computer problems, this is your man. And it's only $19.99, so it's a snip. So, some of the more effective modifications that you use all rely on modifying the Python runtime. As we said, you can distribute the Python runtime in a package. So this means the authors can modify the CPython at the C layer, compile their own version of the Python runtime, and then that can switch things around, make the bytecode that's produced different, etc. And this is what people are doing. So one of the simplest things is to just change that bytecode magic number. You'll remember from the PYC, the first 4 bytes are a magic number that say what version of Python it is. If the Python that you're running isn't the same version, it will bail with a bad magic number error. You probably can't see too well. So these are all the defined magic numbers for the different versions of Python. This is in the comments for the import.c. Basically, all they do is they change the version of the Python number, so any standard Python, apart from their modified runtime, won't run their code. It's kind of, if you fall at this barrier, you're failing pretty hard because you just need to replace the first 4 bytes with a 4 bytes that are standard Python magic number, and you're good. It does make all the standard tools fail because they're, like I say, they're expecting standard formatted bytecode. So it's a very easy change for developers to make, but it's very easy to get around as well. Changes to the marshalling format. As we said, there was the 4-byte magic number, there's a 4-byte timestamp, and then there's this marshaled code. Obviously, the marshalling happens in a standard format. If they go in and go to marshal.c in the CPython runtime and change how it's marshalling things, then obviously all the standard tools won't understand how to unpack it. They can get arbitrarily fancy here. I've seen stuff that looks like it's pretty much they're doing some kind of encryption. I'm sure it's pretty crappy encryption, but still, to work out what they're doing, because it's happening at the CPython layer, you're going to have to trace it in a debugger, and you're going to have to do that for every different type of marshalling modification, which is a bit of a pain, so I wanted to avoid that, and I managed to avoid it by working at the Python layer. We'll talk about that in a bit. And then opcode remapping. This is one of the more complex things that they do. Basically, that table that I spoke of there's integers to instruction mappings, they juggle all that around, so it's not the standard format that you'd expect. They change the opcode.h in the runtime and remove opcode.py from the distributed runtime, and that means that you can get access to the CO code object, but the byte stream makes no sense, and it makes no sense to any of the decompilers because they're running off the standard opcode map, and this has got like a juggled up opcode map. When I found this, it was a real pain, but I've got a pretty simple attack to get around it, which we'll talk about. So the general approach with what we're taking with pyREtic, I want to remove the reliance on having access to the file on disk. I want to work in memory only. I want any of the protections like the marshalling and everything, the application to undo it, because however complex that they've got with marshalling up something, they're going to undo the marshalling, and then when it's in memory, it's just a standard Python object. And obviously, it's easier to understand a standard Python object than piss about at the C layer trying to work out what they were doing with their marshalling. I'm going to get in process at the Python layer, and then obviously I have access to the full Python namespace, and I can start to query the objects, and then from querying the objects in the live memory, get back to a source code representation. So the fact that you can, with a reflective language like Python, query an object, this is obviously really useful in the cloud paradigm because you will never have access to their files. However, Python's a popular choice for using as a sandboxing environment or as an environment to allow you to access their API. They think that maybe if you only have access to their objects, that's all good, but with these techniques you can actually get the source code back from their objects. So even though you're interacting with a remote computer, you can still get access back to the source code even though you haven't got their PYCs on disk, which is pretty cool. Moving forward, I think this is an area that more people are going to have to, for all Cypress languages, not just Python, put more effort into, purely because the paradigms of distributing applications are changing. So I'd expect it to be an area that you'll see a lot more activity in future. So how do we get in process? I said we need to be in process so we can query the Python objects. Obviously, Python, if people are trying to obfuscate their code, they won't distribute the PIs, they'll only distribute the PYCs. And if they've modified their runtime, you need to use their interpreter to run their PYCs because they've pissed about with the marshalling or the bytecode number or whatever. But the import rules for Python still apply. So in import C, you'll see there's this equality test here. We talked about the timestamp, and they're saying this is just saying if the timestamp in the Python bytecode is not equal to the timestamp on the py file that's on disk, then recompile that bytecode. So you're using the py in preference to the PYC because something may have changed in your py, and then you'll recompile the bytecode. Obviously, this test means that you can just, if their module was named foo module PYC, take it to another name, foo original, and then you take your module, the code that you want to run, and just call it foo module.py. Your code will be run in preference. So this is a really easy way to get in process. All the distributors would need to do is take out this equality test, and they would stop people doing it. But I've never seen people have put huge amounts of effort into their remarshalling and things, but they haven't taken out this like 4-line if statement. I don't know why. They fail. So obviously our PY takes precedence, and then because we're running arbitrary Python bytecode, now we can start to query those objects. There's some code that I haven't got on disk, but it's in the paper for blindly mirroring the object that you've replaced, and so you're acting as a proxy between the object that you've renamed and the object which is the code which is calling you, and you're literally passing the calls on into the object. So the code's in the paper. It's pretty useful. That means that the application won't crash. So as I said, non-standard marshalling can be a real pain in the ass. I didn't put much effort into trying to come up with a technique to undo their marshalling because as soon as you're in the Python runtime, they've already undone it. So it was a real pain, so we just completely sidestepped the problem and access it at the Python layer. This is more complicated, however. We've got to remap their opcode. So we've got to work out how they juggled up their opcode mappings, their integer to instruction maps. Obviously, we need to do this at runtime. We don't have access to the opcode.py, so we need to reproduce that opcode.py so all our other techniques can work at the Python runtime. Obviously, we need an understanding of the opcode mapping to be able to get anything from the byte stream. It's this understanding which the vendors are assuming that they've broken. If you don't understand the opcode mapping, you can't get any sense out of a bytecode because it's just a stream of bytes. You don't really understand what it means. But there was a pretty easy way to get at this new opcode mapping, essentially using a plain text attack against the